Swayam Prabha. Digital India. Educated India.
In this lecture, I am going to start the topic of rotation, kinematics of rotation. In this discussion today, I am going to discuss about the rotation matrix and its interpretation and properties of the rotation matrix. What is the rotation matrix? It relates, it is a matrix which relates the representation of a vector in two frames. For example, I have the black frame and the brown frame. The black frame is x naught, y naught, z naught, and the brown frame is x 1, y 1, z 1. Imagine a vector p as shown. How do you represent p in different frames? We drop perpendiculars to the planes. From p we drop perpendiculars to the plane. For example, if I drop it on the x naught, y naught axis, that perpendicular distance from the x naught, y naught axis gives me z naught, and similarly z naught coordinate of p, and similarly I can find out the x naught coordinate, y naught coordinate, etc. I have shown these perpendiculars that I have dropped. This thing that I have written p x super 0, that superscript 0 indicates in which frame the vector is represented. Vector exists by its own right. Vector is an abstract quantity which exists by its own right. Its representation from one frame to another can be very different. For example, velocity. If you have a particle which has a velocity, that velocity belongs to the particle is moving in a certain way. Now, if I choose a particular frame, I will have particular representation of this velocity. If you choose another frame, you will have another representation of that velocity, but velocity is that same vector. It exists by its own right. P is a vector which exists. I can choose to represent in the black frame x naught, y naught, z naught, or choose to represent in the brown frame x 1, y 1, z 1. Here I am showing you first the representation in the black frame p x 0, p y 0, p z 0. The same vector can be represented in a similar manner in the brown frame p x 1, p y 1, p z 1. Therefore, this is the representation of that same vector p in x 0, y 0, z 0. The same vector, and this I will write to differentiate, not that these two vectors are different, but p superscript 0 shows the representation of p in frame 0, just to make it clear, but the vector p, mind you, is the same. Similarly, I can write that same vector p as p x 1 I cap dash plus p y 1 j cap dash plus p z 1 k cap dash. Same vector, but I am, just to distinguish that their representations can be different, I am writing p superscript 1. How do I find p x 0, the x component in frame 0? I take a dot product of the vector p with I cap. What is I cap? The unit vector in the direction of x naught. I cap is the unit vector in the direction of x naught. I take a dot product of p with I cap. This is what I can write. Now, p I can choose any particular vector. If I take dot with I cap, then it gives me p x 0. This I have written already. But if I choose this representation to take that dot product with I cap, this is dot product, then I get I prime dot I p x 1 j prime dot I p y 1, k prime dot I p z 1. Both sides are equal because we are taking dot product with the same vector. Therefore, they cannot give us different things, they must give us the same thing. Similarly, p y 0 I can take dot product with j for both this black and the brown vector representations. I take dot product with j. Left hand side I write for the black vector by taking dot product with j, and the right hand side I have taken dot product with the brown vector and written. Similarly, p z 0. What do we have? We have these three relations, these three equalities. Therefore, the left hand side I can write as a column vector p x 0, p y 0, p z 0, and the right hand side I can pull out p x 1, p y 1, p z 1 and write it as a column vector multiplied by this matrix. And what is this matrix? This matrix, let us look at this term I prime dot I. What does it mean? Unit vector along this is I cap, unit vector along this is I cap prime, and if you take dot product of two unit vectors, it gives me the cosine of the angle between these two vectors. Therefore, this is the cosine of the angle between x 0 and x 1. This matrix is known as the rotation matrix, and it takes a vector from frame 1 to a vector its equivalent representation in frame 0. Coefficients of the representation in frame 1 to coefficient of representation of the same vector in frame 0. This is very important to understand. That we will write as r from 1 to 0. On the right I write 1 because on the right I will post multiply by the representation of the vector in frame 1, and on the left I write superscript 0 on r to show that it is going to take us to the representation of that vector of the same vector in frame 0. And in vector notation we will write p 0 is equals to r from 1 to 0 to multiplied by p 1, and that multiplication is shown. Now, I do the reverse thing. I take dot products with I prime cap. I get this with j prime cap, same steps, but I am now taking dot products with I prime, j prime, k prime of both the vector representations, what was shown in black and brown both. On the left hand side, therefore, I have coefficients of the brown vector in the brown frame, and on the right hand side it gives me it involves the coefficients of representation in the black frame. Again I can represent these two column vector representations of the same vector through this matrix. Now, this matrix looks slightly different, because now I have taken dot product with I cap prime, j cap prime, k cap prime. Initially I had taken dot product with I cap, j cap, k cap. This matrix takes the representation of the vector in frame 0 to its equivalent representation in frame 1. On the right hand side we have representation of the coefficient of representation in frame 0. It takes from 0 to 1, and what we get is a representation of the same vector in frame 1. And again this matrix has only dot products, which gives us the cosine of the angle between the various axes. Let us look at these two matrices together. You will find that the column here is same as the row here. Every column in the first matrix has become a row in the second matrix. In other words, the second matrix is a transpose of the first matrix. The second matrix is a transpose of the first matrix. R from 1 to 0 is transpose of the matrix R from 0 to 1. Similarly, R from, and if you take transpose of both sides of this equation, it will tell you that transpose of the matrix from 1 to 0 is equal to the matrix from 0 to 1. What is the consequence of this? To see the consequence of this, a very interesting consequence, I have written these transformations, once from 1 to 0, other from 0 to 1. Now, these two, for example, this is same as this. So, I can substitute this here. I can substitute this here, and then I get this expression. This is P in frame 1. What does this equation tell us? It must be so that R 1 to 0 multiplied by R 0 to 1 is identity. That is the only way you can have P 0 is equal to P 0. That means R 1 to 0 multiplied by R from 0 to 1 must be an identity matrix. And you know that R from 0 to 1 is nothing but transpose of R from 1 to 0. This also says tells us that R from 1 to 0 inverse is its transpose. This is a very interesting property. This is called orthonormality. The inverse of the rotation matrix is its transpose. So, transpose of a rotation matrix gives us the inverse of the rotation matrix. In other words, if I have this relation, then I can write this like this. I can write it like this, and in a more simpler form I will write like this. Okay, this is the matrix R from 1 to 0. Let us interpret what the columns and the rows represent. The first column I prime dot I, it is nothing but cosine between I prime and I prime dot j, I prime dot k. What is this? This is these are the coefficients of the vector x 1 represented in frame 0. How do I find coefficients of a vector, the coordinates of a vector, let us say position vector? How do you find these coefficients along different axes? I take dot product with the different axes, once with I cap, once with j cap, once with k cap, then it gives me the coefficients of that vector's representation in that coordinate system. Now, what I am doing is I have taken I prime cap and I am taking once with dot product with I cap, once with j cap, once with k cap. What does this give us? This gives us the direction cosines, because they are all cosines of the angle I prime makes with x axis, y axis, x naught axis, y naught axis and z naught axis. Therefore, the first column of this is nothing but unit vector x 1, its representation in frame 0. Similarly, the second column you will find is dot product with I cap, j cap, k cap of the unit vector j prime cap. In other words, it is a representation of y 1 in x 0, y 0, z 0. These are the coefficients, the columns are the coefficients of y 1, unit vector y 1 in x 0, y 0, z 0. Similarly, the third column is a representation or the coefficients of z naught in z 1 in x 0, y 0, z 0, because I have taken k prime cap and taken its dot product with I cap, j cap, k cap. Therefore, I will get the coefficients or the direction cosines of the z 1 axis in x 0, y 0, z 0. In other words, I have this representation of x 1 0, I can write in terms of x 1 in its own frame. What is x 1 in its own frame? What is x 1 in its own frame? X 1 in its own frame is 1 0 0. The x 1 cap vector, the unit vector along x 1 in its own frame, x 1 y 1 z 1. That is the meaning of this representation. This is x 1 axis represented in which frame? Therefore, the representation of the x 1 axis unit vector x 1 in its own frame x 1 y 1 z 1 is nothing but 1 0 0, and if you multiply with r from 1 to 0, it will give me x 1 0. That means, what I am trying to say is, if I multiply this matrix by 1 0 0, it will only filter out this column, and that column is nothing but x 1's representation in frame 0, x 1's representation in frame 0. This is x 1's representation in frame 1, and this one is x 1's representation in frame 0. Similarly, y 1's representation in frame 0 is obtained by multiplying r 1 to 0 of y 1 1, which means representation of y 1 in x 1 y 1 z 1, which will be 0 1 0. That means, it will filter out the second column, and so on. Now, same thing happens with r 0 to 1. Now, what do you find? The first column is the representation of x 0 in frame 1. I have taken I cap, I cap, I cap and taken its dot product with I prime cap, j prime cap, k prime cap. These are the direction cosines of the I cap unit vector in x 1 y 1 z 1. Therefore, the first column of this matrix, which happens to be transpose of the earlier matrix. Now, columns of these this matrix R from 0 to 1 is x naught represented in frame 1, y naught represented in frame 1, z naught represented in frame 1. In other words, because these two are transpose of one another, the rows of this are x 0 represented in 1, the second row of R 1 0 is y naught represented in 1, and the third row is z naught represented in 1, and the columns are x 1 represented in 0, y 1 represented in 0, z 1 represented in 0. So, here I have written how the rows are to be interpreted, rows of R 1 to 0 are to be interpreted. And similarly, of the matrix R 0 to 1, how the rows can be interpreted. Therefore, we now have a very good idea of how the rows and columns of the rotation matrix are to be interpreted. And one more thing to note, when it is R from 1 to 0, then we represent frame 1 in frame 0. This is the x axis of frame 1, x 1 represented in 0, y1 represented in 0, z1 represented in 0. When it is from 0 to 1, we represent x0 in x1 y1 z1, y0 in x1 y1 z1, z0 in x1 y1 z1. So, the columns the definition of columns change, and of course, this orthonormality property holds, and basically orthonormality would mean that dot product of this column with this column, this dot is 0. Similarly, dot product of this column dot with this column is 0. Similarly, dot product of this column and this column is 0, and because now here also similar thing must hold, therefore, dot product of this column and this column, this row, these two rows dot product is 0. Similarly, dot product of this row with the third row must be 0. Same thing for the second row and the third row, that also must be 0. So, any two columns if you take dot product of, it is 0, any two rows you take dot product of, it is 0, but what about dot product with itself? If I take dot product of this with itself, what will happen? These are direction cosines, this or maybe the column, dot product of this column with itself, these are direction cosines, and you know that direction cosines, sum of squares of direction cosines is 1, therefore, these are 1. The dot product of the first column with itself is 1, but the dot product of any column with another column or any row with another row is 0. Dot product of any column with itself is 1, dot product of any row with itself is 1. So, these are unit vectors, always the columns or rows are unit vectors, but they are all orthogonal. Now, if you take determinant of this orthogonality property, if you take determinant of orthogonality property, now this orthogonality property stems from that fact itself, that dot product of any column, any two columns is 0, and dot product of any two different rows is 0, but dot product of a row or a column with itself is 1, and that is how we get this this relation identity. If I take determinant of this equation, this relation, then on the left hand side I have determinant of r from 1 to 0 whole square, because determinant of a product of two matrices is equal to the product of their determinants, and transpose of a matrix determinant is same as the determinant of the matrix itself. On the right hand side the determinant of identity is 1. Now, therefore, the determinant of any rotation matrix can be either +1 or -1. If we consider a right handed coordinate system where the z, the unit vector along the z is cross product of x and y unit vectors, then the determinant choice is +1. Therefore, any rotation matrix with determinant +1 represents a right handed coordinate system. In other words, if you take now the cross product of the first column and the second column, you will get the third column, x cap cross y cap is equal to z cap. Y cap cross z cap will give you x cap, and z cap cross x cap will give you y cap. This is a property of a right handed coordinate system, and for a right handed coordinate system you will have determinant +1. Let us look at this example of rotation about x naught axis. Initially the brown frame was coinciding with the black frame, Now, what we have done is we have rotated the Brown frame, but about x naught or x 1, because x naught and x 1 remain identical during this rotation. Now, how do I construct the rotation matrix? The rotation matrix is constructed by representing, see which rotation matrix we are representing, 1 to 0, which means I must represent the frame 1 in frame 0. Therefore, first column is the representation of x 1 in x 0 y 0 z 0. What is representation of x 1 in x 0 y 0 z 0? You see, x 1 is along x 0, therefore, it must be 1 1 0 0. That is the representation of x 1 in x 0 y 0 z 0. Then we represent y 1 in x 0 y 0 z 0. How do you represent y 1? This is angle phi, I have given the rotation of phi. Therefore, this must be cosine phi, this must be sin phi and unit vector. So, this must be 0, there is no x component, whereas y component is cos phi, z component is sin phi. Finally, the third column is the representation of z 1 in x 0 y 0 z 0. And how do I represent that? There is no component along x, along y it is minus sin phi, along z it is cos phi, that you can check. This is cos phi, and along y it is on the negative side, therefore, minus sin phi. And if you take transpose of this matrix, you will find they are the representations of x naught in x 1 y 1 z 1. For example, this row is the representation of x naught in x 1 y 1 z 1. The second row is representation of y naught in x 1 y 1 z 1, and the third row is the representation of z naught in x 1 y 1 z 1. So, this is r from 0 to 1, and you can now from 0 to 1, because it is 0 to 1, therefore, now you will find that the columns represent x 0 in x 1 y 1 z 1, x y 0 in x 1 y, this is x 0 unit vector in x 1 y 1 z 1, this is y 0 unit vector in x 1 y 1 z 1, and this is z 0, this is z 0 in x 1 y 1 z 1. And you can check that the determinant of these matrices is 1, and the transpose is its inverse. So, this I will leave to you. Let us look at rotation about the y axis. Initially, the brown frame was coincident with the black frame. Now, I give a rotation about the y naught or y 1 axis, and that rotation is theta, and now I represent, because I am representing the rotation matrix from 1 to 0, therefore, I must represent frame 1 in frame 0. This is the column vector, this column is the representation of x 1 in x 0 y 0 z 0, this is the representation of y 1 in x 0 y 0 z 0, this is the representation of z 1 in x 0 y 0 z 0, and that you can check once again. For example, z 1, the last column, what is its representation? This is nothing but cos theta, and this is sin theta, and there is no component along y, therefore, that is 0, along x it is sin theta, along z it is cos theta. In this way, we can populate the entries of the rotation matrix, and the inverse or rotation matrix from 0 to 1 is the transpose of the rotation matrix from 1 to 0. You should check that its determinant of both these matrices is 1, and they are inverse of one another. So, to summarize, we have looked at the rotation matrix, its representation and its interpretation, and looked at some properties of the rotation matrix. With that, I will close this lecture.